Welcome to this lecture series in number theory. We're starting a new module which will be about GCD, or the greatest common divisor. And let's briefly look at what we are going to do in this module. So we will of course discuss what is a GCD, and in today's lecture we'll discuss some very basic properties of it and also look at one interesting puzzle. In the next lecture I plan to talk about the Euclidean algorithm, which helps us calculate GCDs and has theoretical implications. And then I want to discuss Bezout's theorem, and then maybe some other things. So Bezout's theorem is something that I will state and prove, but as of now, let me just plant a flag here. Okay, and as promised, in this module we will revisit the theorem about inverses. We will redefine inverses just for the sake of completeness, and we will prove the theorem about inverses once again. So if A and N are relatively prime, then A has an inverse modulo N, and conversely. So that theorem we'll reprove. We have given a proof earlier, but one more proof is in order. All right, so with that, let us proceed. Some problems for practice. And now let us get started. So what is the definition of the greatest common divisor? It is in the name. So suppose we have two integers, not both of them are 0. If both of them are 0, then no interesting discussion can be done. So assume two integers are given, not both of which are 0. As we have already discussed, a common divisor of A and B is any non-zero integer D such that D divides both A and B. We had seen this definition earlier when we were defining relatively prime integers, but anyway, no harm in recalling. So that's the definition of common divisor. And the greatest common divisor of A and B is the max of all the common divisors of A and B. You collect the set of all the positive common divisors and take the one which is greatest. Since A and B are not both 0, this is a finite set. If A and B were both 0, then every positive integer would be a common divisor, and this would not be a finite set, and hence we wouldn't be able to take the maximum of it, or the maximum of it would be infinity, which is not meaningful in this context. So this is a finite set, and we just take its maximum and call that the greatest common divisor, and it's clear why the name has been chosen. Amongst all the common divisors, we are just taking the one which is greatest, the maximum. So let's look at an example. It's a very simple definition, but let's look at an example. So we have two positive integers A and B. We want to find out its greatest common divisor. So just list out all the common divisors. What are the divisors of 21? 21 has 4 divisors, I think. 1, 3, 7, and 21. These are the 4 divisors of 21. What are the divisors of 15? Again, it also has 4 divisors. 1, 3, 5, and 15. And the common divisors are 1 and 3. Right? The common divisors are 1 and 3. So the greatest common divisor is 3. Another example. Suppose A is 7 and B is 12. What are the divisors of 7? 7 is a prime. It has only 2 positive divisors. So yeah, when I said divisors, when I was discussing this and using the word divisors, I was just referring to positive divisors, although divisors can be negative. Anyway, so what are the 2 positive divisors of 7? 1 and 7. What are the divisors of 12? 1, 2, 3, 4, 6, and 12. But clearly the only common divisor is 1, so the GCD is 1. Okay. And we can extend the definition of GCD to not necessarily 2 integers. We can take any subset of integers where the subset has at least size 2, right? And we can define the GCD of S. So we define the GCD of S. The greatest common divisor of S is, you take the max of all the positive integers which divide each element of S. It's a very simple extension of the previous definition. If you take S as the doubleton A comma B, doubleton meaning a set containing 2 elements. If you take S as the doubleton A comma B, this definition is same as the definition of the GCD as we discussed above. So this just extends that definition, and in fact, it extends it to infinite set. The set S could be infinite, right? So let's take an example. Suppose my set S is these numbers, 3, 6, 9, 12, so on. So all the multiples of 3. What is the GCD of S? The GCD of S is 3. Clearly, 3 is the only common divisor to all of them. In fact, 3 is the only non-trivial divisor of 3. 1 is the divisor of everything, but 3 is the only non-trivial divisor of 3, and it is common to all of them, so the GCD is 3. Right, so it's a very simple concept, and I don't think we need to look at too many examples to digest it. Okay. Some very simple properties of GCD. There are some more interesting and complicated properties. Not complicated, but certainly more interesting. But in today's lecture, we will look at very simple properties. So the first one requires little explanation. If you have an integer a and 1, what is the GCD? What are the positive common divisors? 1 is the only positive divisor of 1, so the only candidate for GCD is 1, and of course 1 divides both, so 1 is the GCD. Very simple. So this is for all integers a. I should have written that. For all, oops. Give me a moment, my iPad is misbehaving. All right. The second property, you take 2 integers a and b, not both 0, then their GCD is same as the GCD even if you flip one sign or you flip both signs. Either you flip one sign or both sign or no signs, it's the same. The GCD is irrelevant. I mean, the GCD is unaffected by changing signs. The reason is very simple. The set of positive common divisors of a and b is exactly the same as the set of positive common divisors of a and minus b, and that of minus a and b, and that of minus a and minus b. So the set of positive common divisors doesn't change even if you change the signs here, and therefore the GCD doesn't change. So let me mark both of them as exercises if you will. Okay, so 2 properties down. Let's look at another one. Yeah, so a and b are relatively prime. So recall what was meant by this notion, relative primality. 2 integers, not both 0, were said to be relatively prime if the only positive common divisor of them was 1. That was the definition of relative primality. We are saying a and b are relatively prime if and only if their GCD is 1. This is just a restatement. This is not a theorem or anything. There is no logical reasoning to be done here, or very little to be done here. So I'll mark this as an exercise also. Just unravel the definition of GCD and you'll see. So the notion of relative primality can be captured by this quantitative notion of GCD. Also, if D is the GCD of A and B, then the GCD of A by D, which is a legitimate integer, because D is the GCD of A and B, in particular, D divides both A and B. If D divides both A and B, A by D and B by D are both integers, and we can talk about their GCDs as long as these are not both 0. Well, since a and b are not both 0, because we are talking about their GCD, we already have implicitly assumed that they are not both 0. So if a and b are not both 0, a by d and b by d will also be not both 0, and hence we can talk about their GCDs. And what we are saying is that if you divide out by the GCD, the GCD becomes trivial. It is a simple statement, but let me prove it. Okay. So suppose e greater than 1, and by e I don't want to confuse you with Euler's number or anything. E is just supposed to be a positive integer here. Suppose e is a common divisor of a by d and b by d. We want to show that, WTST meaning want to show that e is equal to 1. Once we do that, we will have shown that the GCD of these two numbers is 1. In fact, this is precisely what we need to do. We want to show that any common divisor which is positive has to be 1. That is what it means to say that the GCD is 1. So this is what we want to do. But note that e times d is a divisor of a, and e times d is also a divisor of b. Why is that? Well, e is a divisor of a by d. E is a divisor of a by d, and hence ed is a divisor of a. E divides a by d implies ed divides a. Very simple statement. That's what we are using. And by the same token, ed divides b. So ed is a common divisor of a and b, and in fact it is a positive common divisor. Right? So this implies ed, being a positive common divisor of a and b, is at most the GCD of a and b. Because GCD of a and b is the greatest positive common divisor. But GCD of a and b is d. So this implies that ed is at most d, which implies e is at most 1. But e was already at least 1, so this whole reasoning shows that e is equal to 1, and that is what we wanted to do. It's a very simple reasoning, but I did it in full. Okay. Now for something a little more interesting. Not very difficult, but interesting. So yeah, so suppose we have two non-zero integers a and n, and assume that there is some integer x such that this congruence holds. In other words, we are saying that x is an inverse of a modulo n. In the language of inverses, this is precisely what it says, that x is an inverse of a modulo n. We want to show that a and n are relatively prime. And we have done this reasoning before, I remember, but anyway, let's do it again. No harm in doing it again. So here is the proof. Before we go there, fix a positive common divisor of a and n. And we want to show that d is equal to 1. Right? That's what it means to show that the GCD of a and n is 1. Saying that a and n are relatively prime is same as saying that their GCD is 1. So this is what we want to do. Okay, but now by the given fact, since ax is congruent to 1 mod n, we have, by definition of congruence, we have some integer y such that ax equals 1 plus ny, which implies ax minus ny equals 1. Right? But d being a common divisor of a and n, we see that it divides ax and ny. Right? D divides a and hence it divides ax. D divides n and hence it divides ny. So d divides both ax and ny, and hence it also divides their difference. So d divides the left hand side, and hence it also divides the right hand side. So d divides 1. So d being a positive integer divides 1 means that d is equal to 1. So I don't want to write it down. I have said it in words. This implies that d is equal to 1 and we are done. Very simple reasoning, but we have done it. In fact, if you remember our discussion on inverses, this implies that there is such an x. So the converse of this lemma is also true. That was the difficult direction of the inverses business. Right? I'm just kind of redoing part of the discussion that we've already done in the previous module. Anyway, I hope you follow this reasoning. And here is a very nice lemma which I will attribute to Euclid because this is basically what he used to prove the infinitude of primes, which we will get to later. So what are we saying? We are saying that fix a finite set f, then there is some natural number y. So fix a finite set f of natural numbers. The finite set is containing only natural numbers. We are saying that there is some natural number y which is relatively prime to every element of f. Right? For example, suppose f had only one element. Let's say f had some natural number a. Then can we find such a y? Clearly we can. Just take a plus 1. A plus 1 will be relatively prime to a. Why is that? If d is a common divisor of a and a plus 1, if d divides a and d divides a plus 1, then d will also divide their difference. So this would mean that d divides 1 because 1 is the difference of a plus 1 and a. But d dividing 1 implies that d is equal to 1 because d is a positive common divisor and hence the GCD of a and a plus 1 is 1. So when f is a singleton, it is trivial or slightly non-trivial if you will. We want to prove it for general finite subsets. And here is the way. Here is Euclid's way. There are many ways, I'm sure, but here is how Euclid did it. So all he says was, take the product of all the things in f. So this is just a fancy way of writing the product of all the things in f. Product of all the things in f. And that is what capital N is. And just take y or define y as n plus 1. Okay. So then note that, fix. Okay, so let me write it in full, although it's a little bit of a waste of time. So we claim y is relatively prime to each element of f. And here is the proof of claim. Fix some element of f. Then note that n is congruent to 1 mod a. And thus, so why is n congruent to 1 mod a? Well, not n, I meant y. What am I saying? Y is congruent to 1 mod a. Why is y congruent to 1 mod a? Because a divides n. This is how n was defined. Any element of capital F is going to divide n. That's how n was defined. So a divides this guy and therefore y is congruent to 1 modulo a. So this happens. And now if we use the previous lemma with y playing the role of a and x being equal to 1 and n playing the role of a, it's kind of perverse notationally. But I'm sure you follow that this implies that GCD of a and n is 1. Sorry, a and y is 1. What am I saying? So that's it. I mean, it took a lot of time proving something very simple. I could have ended the proof here. Right? So just note that any element of f is congruent to 1. Any element of f you take, call it a, then y is congruent to 1 modulo a. That's all. So I hope you follow. I mean, it's a very simple piece of reasoning. I think, no, I have one more slide. So it's a simple puzzle. Fix an infinite subset of natural numbers such that the GCD of them is 1. As we discussed, we can define GCDs of infinite subsets also. Just collect all the positive common divisors and take the maximum. Then we want to say that there is a finite subset of S whose GCD is 1. If an infinite subset has no non-trivial common divisor, then there is a finite subset of it which also witnesses the same fact. Okay? So try it out. Try to solve this yourself. Pause the video and try to prove it. And here is what we will use. I'm going to write down a proof, and here is what I'm going to use, which is an exercise. It looks a little complicated, but it is nothing. What we are saying is that suppose we have an infinite sequence of natural numbers, n1, n2, n3, which is decreasing. Not necessarily strictly decreasing, just decreasing. n1 is at least n2, is at least n3, and so on. We want to say that this ultimately becomes a constant sequence. Ultimately. Meaning after a certain point, you will not see any change. So the precise formulation is that there is some capital K, some index capital K, such that beyond that point of time, beyond the time K, all the values are the same. Note that it is important that these are natural numbers, not integers. This statement would be not true if I replace this by integers for obvious reasons. Right? Basically, natural numbers have a lower bound. You cannot go below 1. So this is a very intuitively obvious statement and very easy to prove also. So I encourage you to prove this, and we will use this. And we will write down a very formal proof for this fact. So, say the set S is, we can arrange the elements in increasing order, and this is a slightly sloppy way of writing, but I will explain. Any infinite subset of natural numbers has a smallest element, as a next smallest element, as a next to next smallest element, and so on. So that's all we are saying, that these are I've just arranged the elements of S in an increasing order, that's all. This is not really how you write a set in roster form, but whatever. Okay, so define. So let D1 be all divisors of, maybe I'll be even more formal, so, or whatever, all divisors of S1, all positive divisors of S1. D2 is the set of all positive divisors of S1 and S2. D3 is all positive divisors of S1, S2, and S3. And so on. Right? We have just collected the sets, or we have defined the sets of positive divisors of more and more elements of the set S. And clearly, D1 contains D2, which contains in turn D3, and so on. Correct? Simply because if you have an element in D2, that is also there in D1. If something divides both S1 and S2, it clearly divides S1. So this is an obvious statement. Okay, and what are we given? We are given that the set of all the common set of the set which consists of the positive common divisors of all elements of S is a singleton, namely it contains only the positive integer 1. Right? What does this mean? It means that, or let me write it. So since GCD of S is 1, we have by definition that the intersection of all these DNs is a singleton. So this contains only one element, namely 1. That's exactly what it means to say that GCD of S is 1. This is the set of all those positive integers which divide each element of S. That's what this is. And since GCD is 1, it just means that this set has nothing but the element to 1. So we are given this. Okay. And now by this exercise and by this containment, if we let me not write an n here, let me write a k just for notational convenience. So say N1 is the size of D1, N2 is the size of D2, maybe I'll write it here, N3 is the size of D3, and so on. So we clearly have these inequalities. Since this is a chain of containments, it follows that the size will not increase. The size of D1 cannot be less than the size of D2, which cannot be less than the size of D3, and so on. So we have that. Now if we use this exercise, we know that this eventually stabilizes. This sequence eventually becomes constant. Now if that value, if the value of that constant is greater than 1, then what does that mean? It means that this stabilizes, meaning after a certain point, these sets do not change. Or regardless, since these numbers eventually stabilize, they eventually become constant, we know that this eventually becomes constant because these are containments. The sizes of these sets, if after a certain point they do not change, because of this containment relation, the sets do not change. For instance, suppose I told you that the size of D1 is the same as the size of D2, that immediately implies that D1 is equal to D2 as a set. Because D2 is contained in D1 and because D2 and D1 are finite sets, the fact that, or the information that D1 and D2 have the same size implies that the sets are the same. So by this exercise, since this sequence eventually stabilizes, and by the small piece of reasoning that we just gave, we know that this sequence ultimately stabilizes, meaning after a certain point, all these sets are the same, right? So what is the intersection of all of them? Whatever that same set is, whatever this chain stabilizes to. So after a certain point, all these sets become, let's say, D. So the intersection of all of these will also be D. But we know that D is just this set, singleton. So that's it. After some finite point of time, let's say capital K, these sets all of them become D. So the kth set is D, the k plus 1th set is D, the k plus 2nd set is D, and so on. So the intersection of all of them will be the set capital D. So this is the set capital D. And therefore the set capital D is the singleton one. And therefore the kth set here is the singleton one. And that's it. That shows that the GCD of the first k elements of S is 1. Because the set of all the positive common divisors of those k elements is a singleton, namely 1. So that's all. I mean, I took a lot of time on this, but I hope you follow. It's a simple puzzle. It's not a complicated thing. Maybe the writing and the explanation makes it look complicated. At any rate, I encourage you to stay on it if it is unclear. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.